Hi, today I want to give you a overview of nuclear magnetic resonance spectroscopy, also known as NMR. And I thought I'd just go to ChemWiki at UC Davis. They got a great page here. It's quite detailed, so if you want more information, this is a good place to go. But what I thought I'd do is just kind of borrow some of the graphics that they have on this page. And first of all, nuclear magnetic resonance spectroscopy is an experimental technique that you basically can analyze certain nuclei because they have spin. And without getting into too much physics, you can kind of consider the nuclei of certain elements as a small magnet, and they can have a north pole and south pole associated with this nuclear spin. And over here are the elements that are most important to us in organic chemistry. There they are. H1, which is good because hydrogen, the first isotope of hydrogen, is very common. C13, organic molecules have lots of carbon. Unfortunately, it's the 13th isotope that's NMR sensitive. It has the spin we need to observe NMR. And C12 is NMR silent. It doesn't have a spin, or a spin is 0. And then there's also fluorine and phosphorus, which can be of use in some systems. But anyways, it's got carbon and hydrogen. We can use that. And we'll talk more about the fact that the less abundant isotope of carbon is used in carbon NMR. We'll discuss that in class. But here's the main idea. We consider each nuclei, and carbon, it would have all 6 protons and 7 neutrons in C13. Consider it as one object, the nucleus of an atom, and it's spinning, and that generates a magnetic field. Now if we put the nuclei in an external magnetic field, just between the bar magnet, or maybe a horseshoe magnet, so you can get the nuclei inside the magnetic field, then the nuclei has two choices. It can spin with the magnetic field facing up. That's what this first case is. The north pole's up, aligned with the magnetic field. Or it can do the opposite. It can actually flip its spin and point the north pole down. And of course, that's not very stable. That's the more energetic spin state. And that's what this graph down here is illustrating, that the energy of the nuclei is proportional to the strength of the magnetic field. Meaning, as this magnetic field gets stronger, the energy difference between those two spin states gets wider. And what's interesting is that if you look at the lower energy spin state, and you can zap that with some radio waves, if the radio waves have the exact amount of energy that bridges this gap, they can flip the spin. The radio waves will be absorbed, and the nuclei will flip its spin so the north pole is facing down. And then what can happen is the nuclei act like little gyroscopes, and they can precess. You can look that up on the internet if you like, and they got some neat little videos showing how, like a spinning top, a gyroscope can actually kind of flip upside down and right itself. And the nuclei do that too, and they can re-emit the radio waves as they go from spin down back to spin up. Anyways, that's the key principle. The nuclei behave like little magnets. Put them in a magnetic field and shine them with radio waves, and we hit the right frequency and we get the spin to flip. Okay, so here's that diagram again. Two different field strengths. Let's see if I got the pin here. Good. So here's spin state 1. I'm sorry, not spin state, but the magnetic field strength is pretty low here. So the energy difference only between these 2 points. So you increase the magnetic field. Now the energy difference is larger. And again, if you shine radio waves with the right frequency, they'll have the right amount of energy, and it can flip the magnetic moment from spin up to spin down, and that's an absorption of energy. The nuclei gain that energy so it can do the harder task of being upside down, and then later the nuclei can relax, flip back to the normal state, spin up, and release that energy again, and actually emit radio waves. And the NMR spectrometer can pick up those two phenomena. You can either shine radio waves and we can watch the absorption of radio waves, or we can wait for the flips, the nuclei, to re-emit the radio waves and pick those back up again. Okay, so in a nutshell, that's the phenomenon that we're exploiting in NMR spectroscopy. Now here's the nitty-gritty. What we get is data that looks like this spectrum here. Let's scroll down over here to the workings of an NMR. Essentially, this is how it works. We put the organic compound, usually dissolved in a solvent, inside a test tube, a very narrow test tube, and place it between the poles of a magnetic field. Right? So we have to get a external magnetic field, and so we put in either an electromagnet or a superconducting magnet to get a very strong magnetic field. And then we got some coils here that both emit radio waves and detect them, see which radio waves have been absorbed. And that's all the idea is. Just shine some radio waves while the molecules are in this magnetic field, and if we hit the right frequency, then we can get some radio waves being absorbed, and we can figure out what frequencies were absorbed and get some data. And the data looks like this. Okay, let's see, there's two things going on here. First of all, you have to tune the NMR to the particular frequency of your nuclei. So let me go back to the web for a second here. Scroll down on ChemWiki, and there's a little plot over here. Here's the frequency corresponding for different nuclei, and it turns out that the magnetic field corresponding to each nuclei is different, meaning that they will spin flip at different frequencies, different energies, even though the magnetic field is staying the same. Okay, so if you want to look at carbon NMR, you need to tune your magnet to a particular frequency. If you want to look at hydrogen, proton, you have to tune it to a different frequency. Okay, so that's the first thing you have to do. Choose your nuclei and go and look at it with the right frequency of radio waves. Then the second thing can happen here that makes it useful. Here the magnet's been tuned to hydrogen nuclei, and we have a mixture of two compounds in this spectrum. We got this molecule called TMS. It's a reference compound. Typically you put that in every NMR spectrum we take, and the idea is it's got a nice symmetrical molecule, lots of hydrogens, 12 total, and they all contribute to a single peak, this little bump down here. We've got some other hydrogens in our compound. We got the hydrogens that are connected to a methyl group right next to an oxygen. And then we have a second methyl group that's connected to a carbon, and we do get different peaks. We get a total of 3 depending on how that methyl group is situated. Okay, what's happening here is that in addition to the changing magnetic field of your magnet in the NMR, that can change the energy levels, right? So you use a stronger magnet, makes the energy gap bigger, changes the frequency. So that's one phenomenon. The other phenomenon is that the electrons in the molecule, mainly these chemical bonds, and the electrons in the adjacent atoms, those electrons also have a magnetic field. And typically, the electrons' magnetic field is opposite the external field. And so what that does, it tends to shield the nuclei. It brings down the field strength, right? So the B is the usual symbol for magnetic field. The effective magnetic field of each hydrogen is equal to the external field, so the NMR's magnet, the external field, and then that magnetic field is reduced in strength by the electrons that are nearby that nuclei. Okay, and so the more electrons adjacent to the hydrogen, the less the field strength. There'll be a smaller effective field strength. Or in other words, silicon is less electronegative than carbon. So there's actually a little dipole moment here where silicon and carbon are actually making a polar covalent bond, where carbon is more electronegative and it's pulling electrons away from silicon. And that means silicon's electrons are gathered around the methyl group and is starting to shield these hydrogens from the external field. And that causes the frequency to go upstream or upfield, and we get a frequency over here. And we just calibrate the NMR so that wherever TMS is, we call that our 0 point. Now these methyl groups are losing electrons, right? So oxygen here is very electronegative. Carbon relative to that is electropositive. The electrons are flowing away from the methyl group, leaving the hydrogens naked, if you will, and not shielding them. Okay, so this term is getting really small, and these hydrogens here are feeling nearly the full strength of the external magnetic field, and so they get shifted downfield over here. And they're absorbing at a different frequency because their effective magnetic field is larger. And then over here we got this methyl group. It's adjacent to this carbon, which is a little ways away from two oxygens. And so these electronegative oxygens are pulling electrons away from this methyl group, and it shifts that peak down here away from TMS. But it's not shifted so far downfield because it's not adjacent to the oxygens. Not like this one is very adjacent, very close to the oxygen. Okay, so to review, the NMR is going to give us peaks, and the peak positions are going to tell us something about where these hydrogens are in the molecule. Furthermore, you can retune the NMR so it can look at the carbon atoms, and you get different sets of peaks. And again, the carbons will absorb at different frequencies depending on where they are in the molecule relative to other electronegative atoms. Okay, here's some terms you should be familiar with. I already mentioned upfield and downfield, and again deshielding and shielding. We always have our calibration peak with TMS, and sometimes you hear the term high field and low field. ppm sometimes is written as a delta, but what that, sorry, writing off the page there, delta, your book defines that, and it's basically just a scale. What we'll be familiar with is anytime the scale runs from around 0 to 10, that's the hydrogen NMR. And when the scale, let's see if I got one, that runs to 200, going down, here we go, well, let's go down here. Here's one where the scale runs from 0 to 200 or so, that's tuned to carbon, and that'll be C13 NMR. Each hydrogen producing a peak, but they're all equally deshielded. They're all equally the same distance away from the oxygen, and they all contribute to the same overlapping peak. Sorry, talking about these hydrogens now. They're all the same distance from the silicon, so they all resonate at the same frequency. These hydrogens are the same distance. Each hydrogen of these three is the same distance from this oxygen, so they all resonate at the same frequency there. Two more items that we'll just kind of briefly talk about. Over here we got cyclohexane showing the chair conformation. And we got an axial hydrogen here, and we got an equatorial hydrogen here. And we talked about how the axial position is more crowded and not as stable, and the reason for that is that the axial groups are actually relatively close, which means their electrons are close, which means these hydrogens are going to be shielded by these bonding electrons here. Whereas equatorial hydrogens are pointing away from the ring, they're farther away from those electrons, and they're going to be deshielded to some degree. The bottom line is that the axial and equatorial hydrogens should produce different peaks. And we do see different peaks at low temperatures. However, at room temperature, 25 degrees, we only observe one peak. And the reason for that is that the cyclohexane ring is rapidly chair flipping, right? So what was axial then becomes equatorial. And when it's equatorial, it absorbs at one frequency, and when it's axial, it absorbs at another one. And if the molecule is flipping back and forth quickly, like it does at room temperature, then you only observe one peak. It's an average of the two. But if you cool the molecule down so it doesn't flip very quickly, well then you can see two peaks. They're separated. And so this actually gives you some interesting kinetic information. And from this temperature information, the fact that you see two peaks, you can actually get some interesting information, such as the activation energy for the chair flip. Okay, so the chem majors, take note, that's something interesting you might see in an advanced course. Now, because we typically use more solvent than compound when we prepare our samples, the NMR will actually be overwhelmed by the presence of normal hydrogen, and so what we typically use is a deuterated solvent. So substitute normal hydrogen for hydrogen with an extra neutron, deuterium, and it turns out that regular hydrogen absorbs a frequency different from deuterium. And so using a deuterated solvent, such as chloroform, which has H2 in it instead of normal hydrogen, protium, will give you a signal of frequency that's outside the normal range of 0 to 10, which means it's typically invisible. Okay, that's a quick introduction to NMR spectroscopy. Key features are we're shining radio waves on these molecules, and because we can detect the radio waves being absorbed, that gives us information about where these atoms are located in the molecule. We can find out how they're connected together. More about this in class. See you soon.